All right, welcome. In this video, we're going to be going over our quiz. This comes from ACE Physics paper 21 from 2017, May, June. We're going through questions 2 and 3. Question 2, state the two conditions for a system to be in equilibrium. And just a moment ago, we heard that there is no net force and no net torque. And so another way of saying like there's no net force is to say, well, what is the net force equal to? 0. So you can word it like that. You can say the net force equals 0, the net torque or the net moment equals 0, or you say there is no net force. So no net force, no net torque. I think that's just a convenient way to sort of memorize it. No net force, no net torque. But then you could maybe think about putting that into more formal language if it were, a physics paper, say, the resultant force, on the system is 0. The resultant torque or the resultant moment, you can use, either one, on the system is 0. So to be in equilibrium, there can't be any net force or there can't be any net torque. If there were a net force, we know it would accelerate according to Newton's second law, and an accelerating thing is not an equilibrium, or a rotating thing, right? So like if there's a net torque, then it's going to spin in the direction there's a net torque. 2 marks for that one. And you could, as long as you worded something that's equal to that, you're in good shape. Here we have our paraglider P of mass 95 kilos pulled by a wire attached to a boat as shown. The wire makes an angle of 25 degrees with the horizontal water surface. It says P moves in a straight line parallel to the surface of the water. The variation with time t of the velocity v of P is shown. Figure 2.2, so that's given there. So it looks like there's some constant velocity going on initially for the first 4 or so seconds of motion, maybe exactly 4. It's hard to kind of see that. I think that is exactly 4, right? So right at 4 seconds, there's this increase in velocity. Okay. Show that the acceleration of P is 1.4 meters per second at time t equals 5 seconds. Let's first sort of extract what we need to out of the plot. Like let's look at 5 seconds and see what sort of information we can glean from the figure there. And they tell us the answer, show that the acceleration is this value. The one thing to sort of keep in mind is that acceleration, when we're looking at a velocity time graph, is the gradient, is the slope. And so if you thought, oh, I should take the slope of this line at 5 seconds, that's like here. It looks like the velocity is right at 6. Like 5 seconds corresponds to 6 meters per second of velocity. But the acceleration is the slope, right? The rate of change of velocity. So you could sort of think about that as a single data point and then try to find another one. This looks like a pretty constant slope, so it shouldn't really matter what points we use. Let's zoom in and enhance to make our life just a little bit easier. All right, so here we've got 4, and then there's 10 squares, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, so 1, 2, 3, 4, 5, halfway. It goes all the way up to here, corresponding to 6 meters per second. You guys ever watch the Price is Right? You got the yodeling guy that like goes down the mountain. He's like, it's like yodeling down here until we find a good data point right there. That's corresponding to 6 point, it's each 1.4 because it goes 4, 4.4, 4.8. Nope, it goes 4.2, 4, 6, 8, 5. Yeah. So 5.2, 5.4, 5.6, 5.8, 6. So each one is 0.2. So 6.2, 6.4. 8, right? So at 6.4 seconds, it was going 8 meters per second, but way back here at 5 seconds, it was only going 6 meters per second. So I just kind of write out my coordinates, right? These are the times, 5 seconds, 6.4 seconds. These are the velocities, 8 meters per second, 6 meters per second. We can remind ourselves that acceleration is the rate of change of velocity, the change in velocity over the change in time, or v minus u over t. And really, we could kind of think about that like v minus u over like t2 minus t1. So like the velocities corresponding to these times. Or you just think about it like it's the slope, and it's, you know, y2 minus y1 over x2 minus x1, except for these aren't x's and y's, they're t's and v's, right? So it's like, but this is like more of a math class, you know, we're more familiar with this from math class, but we just have to connect it like, oh, we're doing the same thing. So it's the difference in the velocities, which is like this y coordinate minus this y coordinate, if you like that. 8 minus 6 meters per second, these are both meters per second, right? Over 6.4 minus 5 seconds, right? So meters per second are meters per second squared. Those are good units of acceleration. And we get 2 over 6.4 minus 5 is 1.4. So 2 meters per second over 1.4 seconds is 1.42857, which is indeed about 1.4 meters per second squared. Now we zoom out, scroll down. There we go. Show that the acceleration is 1.4. And that's how you do it. You have to take the slope of that part of the graph. You didn't have to use the points that I used, but you can see that they work out to show that. You know, we only kind of played the little Yodeling man game down the slope until we found, you know, I found a good point that I liked, but you might have found a different point. As long as you can read off the coordinates, you're good. And that's the same thing we do with our lab work every week, right? So it's a useful skill to be able to have. So 2 marks for that. You know, some kind of working like this where you're able to calculate the slope. Now, the only way you could have gone wrong is if you didn't choose points on this, like if you would have calculated it to be 0, well, then you didn't pay attention because it said at t equals 5 seconds. So like anywhere within here, that's the constant acceleration, right? Like it's constantly increasing the slope there. So you could choose at any points on this part of the graph, but you couldn't have chosen points before 4 seconds here, right? If you chose points down here, you would have got 0, and that's not right. 1.4. Calculate the total distance moved by p from 0 to 7. So now we need the distance moved. All right, so 7 seconds is 6.24687, right there. So we've got 6.24687. There's our 7 seconds, and this is going up to this point right here. It looks like that's a velocity of, how do these go up? Just by, they have to go by 0.2, 6.2, 6.4, 6.8, 7, 7.2, 7.4, 7.6, I think I did it. 2, 4, 6, 8, 7. 2, 4, 6, 8, 8. Yeah, so these go up by 0.2 also. So this is 8.2, 8.4, 8.6. This is 8.8. So we need to calculate the distance traveled, distance moved. It's the area underneath this curve. Okay, so it's like the area of this I guess funny looking trapezoid. I guess that's a trapezoid, right? Okay. And so you might break it down into like this rectangle here, and then this triangle right here. That's one way to sort of calculate the area. You could maybe try to use equations of motion and say, well, let me just calculate like this box over here when it was moving at this constant velocity, and then, you know, calculate what was the displacement of an object that goes from, this is 4.2, this is 4.6. So that was its initial speed. But it accelerates from 4.6 meters per second up to 8.8 meters per second over 3 seconds. So like this is the accelerated part of the motion. So you could use an equation of motion here, which again is the same thing as taking the area underneath the curve and then just add it into this. So let's kind of think about it like this. For the first 4 seconds, this person is just coasting along at 4.6 meters per second. So the distance that's traveled is the velocity times the time. It's just taking velocity equals distance divided by time and making the distance the subject. So we were going 4.6 meters per second for the first 4 seconds of motion, which means we covered 4.6 meters every second times 4 seconds gave us 18.4 meters, right? Seconds cancel, I got meters, that's just the area of this part. Now let me think about solving the area underneath this part of the graph by considering like the S equals UT plus 1/2 AT squared, right? The distance is, so I was already going this initial speed, 4.6, right? That's my initial velocity. But then I'm only looking at this leg of the motion, right? I've already accounted for all of the distance I've covered going at the constant velocity 4.6. Now it's the accelerated part. So I'm only sort of worried about from 4 over. So I was going 4.6 meters per second initially over these 3 seconds here. So the correct time to plug in for this one would be 3, okay? Because it's these 3 seconds from 4 to 7. Plus 1/2, what should I plug in for acceleration here? Anybody know? Oh, I just saw somebody type it down in the comments on YouTube in the future. Good job, whoever it was. 1.4 meters per second squared. You're following along as we did that calculation previously, right? That's the acceleration we just calculated at 5 seconds. Well, that's the constant acceleration all throughout this part of the motion, right? So we know the acceleration. We already calculated it. In fact, even if we didn't calculate it, they told it to us. They're like, show that the acceleration is this, right? And that's still over these 3 seconds. Like it was accelerating constantly for these 3 seconds. And so this term captures this triangle, right? That's 1/2 base times height. The base, you know, V minus U is the same thing as AT, and then times this T. So 1/2 base times height. And then this rectangle down here is this term, right? That's our length times width, 4.6 times 3. So it's like this area is here, this area here, this area here. So now I just got to add them all up, right? So we got 18.4 meters right here. This term right here, 4.6 times 3. So the area underneath this would have been 13.8. And then the area of this triangle is, you know, this term right here. So 0.5 times 1.4 times 9. 6.3. So the total displacement should be 6.3 plus 13.8 plus 18.4. Hopefully when we look this up in the mark scheme, we'll see that the total displacement or distance traveled is 38.5 meters. I'm sure, I know there are other ways to solve this. Okay, so if you got this answer, but you did it some other way that was clever, awesome. Like that's good that there's multiple paths to the same correct solution that people think differently on the same problem. All right, so this is just the way I decided to do it. And if I did it again tomorrow, I might decide a different way. Keep practicing with it. So 38.5, and I might even say 39 or 40. Let's say 39. So that's part 3. Calculate the total distance moved. I'm going to give it 38.5 meters. Did anybody get that? No? That's a tough one. Okay, keep practicing with it. Calculate the change in kinetic energy from 0 to 7. So the change in kinetic energy is going to be, let's solve it like this. Change in kinetic energy equals the kinetic energy final minus the kinetic energy initial. And that's the change in kinetic energy. The final kinetic energy is going to be 1/2 mass times the final velocity squared. The initial kinetic energy would have been 1/2 mass times the initial velocity squared. If we really wanted to, I suppose we could write it like this: 1/2 m v squared minus u squared. That might make it a little bit easier to do the calculation. Does anybody remember the mass? It was like 95 kilograms. We'll go look it up. The final velocity, remember, was 8.8 meters per second. Start out at an initial speed of 4.6, I want to say. Was it 4.6? Help me out, guys. We just used it a moment ago. I think it was 4.6, right? 4.2, okay, 4.6. So this should solve it. All right, the change in kinetic energy. It should be the same if you just put 1/2 95 times this number squared minus 1/2 95 times this number squared. You could factor that 1/2 m out or leave it in there. 8.8 squared minus 4.6 squared gives me 56.28 inside the parentheses times 95 times 0.5. I'm getting, I'm on the wrong part of the paper. All right, I'm getting a calculator value of 2673.3. So we should maybe call this 2700 or 2.7 by 10 to the 3. So one of those answers. I think we'll check it in the mark scheme in a second. Now it reads the tension in the wire at time t equals 5 seconds is 280 newtons. Calculate for the horizontal motion, for the horizontal motion, the vertical lift force F supporting P. So let's click that calculation out. All right, so we had the tension in the wire. So remember, the wire was like this, and it was 25 degrees. And there was like a paraglider right here, and they're telling us the tension in this wire is 280 newtons. All right, and at t equals 5 seconds, so we've already calculated something for that. Remember, that's when this thing is accelerating at 1.4 meters per second squared. So remind yourself, this is part 4 of this lengthy calculation. One calculation leads to the next, and so it's not an accident that we're looking at the same time that we've already sort of examined. Calculate for the horizontal motion the vertical lift force supporting P. Okay, so you've got a paraglider here that has mass. It's got mass, it's got weight. Weight goes this way down. So if you've got weight mg equal to 95 kilograms times 9.81 newtons per kilogram here on planet Earth, how many newtons of weight do you possess? So 95 times 9.81 would give you a weight of 931.95 newtons. And the up's got to equal the downs, okay? Let's read through this very carefully and make sure we've got sort of permission here. So it says, State two conditions to be in equilibrium. A paraglider of mass 95 is pulled by a wire attached to a boat as shown. The wire makes an angle with the horizontal water surface, angle 25 with the horizontal water surface. P moves in a straight line parallel to the surface of the water. Okay. They're moving in a straight line. The velocity then is this direction, right? Like the velocity vector is going straight horizontally. We're only accelerating in that direction, right? We're accelerating in the x direction this much. So like this boat just sped up, okay? So it was going 4.6, then it speeds up after 4 seconds and it starts going faster. The tension in the wire is given, okay? So this tension has a component that's going up, right? It's like, in other words, the vertical lift force supporting P, how does that relate to the tension here? So there must be a component of tension that's acting vertically and a component of tension that's acting horizontally, right? Because the wire is going at 25 degrees above the horizontal. So this paraglider has weight, okay, that's acting down. The tension in the wire kind of goes like it pulls sort of, you know, it's pulling sort of the person along this way. So imagine if you cut that, what would happen? There'd be a lift force, okay, from like the parachute that's like, would make this person sort of, fly up into the air, right? So there'd be sort of a lift force, and the tension in the wire is partly sort of holding the person down. So the person has weight acting down and a component of tension, right? It's like the wire has tension that goes, down and to the right, like the tension sort of like pulling the person along sort of this way. You can imagine, sort of pulling back. You have both the weight of the person and the component of tension acting down that must be balanced by the lift force this way. So the question is a little bit tough because you don't just have the weight of the person balanced by lift. I think you also have a component of tension in the wire that's contributing to that. Okay. How are we doing? So you have to resolve that vector here, and so we can do that real quick. We'd have the down component of this 280 newtons. 280 newtons is the tension in the actual wire going this way. So there's a component that's sort of opposite that 25-degree angle. So the sine of 25 degrees times 280 newtons. Plus, remember, this person had weight of 931. So like if you all of a sudden stopped moving and a person is just, sitting there, they're going to fall down due to their weight, right? That's going to sort of act down. So their weight is a force that always acts down. There's a component of tension that's sort of pulling the person down to combat the sort of lift that's going up, and lift is what we're trying to calculate. This is the way we need to kind of think through it. 931.95 plus 25 sine times 280, 118. So I get a total of 1050 newtons. That would be acting down, and so the lift must be sort of equal to that because we're not sort of have any velocity vertically. We're not moving vertically. So I think a good answer would be 1050. Calculate for the horizontal motion the vertical lift force F supporting P. So 1050 newtons for that. The force R due to air resistance acting on P in the horizontal direction. So now we're thinking about what's the drag force R. So you had the paraglider P, you had them moving along this way with a velocity, with an acceleration, right? They're accelerating in this direction at 1.4 meters per second squared, which means there's a net force in that direction to cause that acceleration. The net force is always equal to the mass, which we know is 95, times the acceleration, which we were given 1.4 meters per second squared. So if we take our 95 kilos times our 1.4 meters per second squared, we can realize that the net force is 133 newtons, okay, in the horizontal direction, because that's the direction that we're sort of moving in, we're accelerating. So if there's 133 newtons of net force, and we had a wire like this that was 25 degrees above the horizontal, had 280 newtons of tension in it during this time, the net force is going to be in the direction of motion, right? We're accelerating in that direction. We have a resistive force that's opposing that, and we have like this force from the tension that's pulling us along, right? Like that's the force that's making us actually go in that direction. Because think about it, if we didn't have that cord there, we wouldn't keep moving with the boat, right? So like it's the tension that's sort of pulling us along in this direction. So what is the cosine? Because this side is adjacent, right? So what's the cosine of 25 degrees times 280? That would give us the component of tension that's pulling us along, pulling the paraglider along. So we take 25 cosine times 280, and we realize that's a force of 253 newtons, but there's only a net force of 133. Okay, so let's the sum of the forces is equal to 133 newtons, right? Because that's m times a. But the forces there are the horizontal component of tension, and then the resistive force of drag that opposes it, right? There's an air resistance that sort of slows you down. So the horizontal component of tension, we calculated to be 253 newtons. And this is where we kind of went wrong yesterday towards the end of class. We were rushing through, and I didn't take the time to like set it up formally like this. And so I think like I added, I should subtract or something. So it's 253 minus the resistive force to equal the net force. The negative sign comes from the opposition of these vectors, right? Here's our paraglider pulled along at this, some resistive force here for a net force of 133, producing the acceleration that we know we have, 133. So if we add R to both sides and then subtract 133 from both sides, we'll have solved it. And so R is just 253 minus 133, or 120. That was a really tough one, okay? And hopefully we learned something by going through it here, even if you weren't successful when you first sort of attempted it there. There's no doubt about it, that's a pretty tricky one. You gotta really kind of have studied it for a bit and be more familiar, like working with forces to make good sense of it. So a lot of practice with this will help you become more proficient with your calculations. And then there was question 3 rather. It says a cylinder is made from a material of a given density. The cylinder has a diameter of this and a length of that. Show that the cylinder has a weight of 0.60 newtons. All right, we got 8 minutes left in class. Here we go. If we're given the density, that's mass per volume, and we're trying to show the weight is something. And so if we can sort of get mass, then we're one step away from weight. So mass would just be the density times the volume. We kind of talked about this yesterday. The density is 2.7 grams per centimeter cubed. We've got a cylinder that has a diameter of 2.4 centimeters and a length of 5 centimeters. And so what's the volume of this? We could say it's the area of the base, the two-dimensional area, which is a circle, so pi r squared, and then times the length, L. So it's going to be, and it's in centimeters cubed, and so these are in centimeters, so no need to sort of make life harder on ourselves. We'll just go, the volume here is pi times r, which would be 1.2 centimeters squared, pi r squared times 5. Then we'll get our centimeters cubed, right? Multiply all this, that'll cancel out, will be in grams. So the units are really important, you know, like write the units out to help avoid making mistakes. So let's in our calculator now take the product of 2.7 grams times pi times 1.2 squared times 5, and this gives us 61 grams. That's the mass, right? So centimeters cubed cancel. And to calculate the weight, we need mass times gravity, but newtons of weight means we need kilograms of mass. So you should plug in 0.061 kilograms, right? Divide this by 1,000, remove the decimal point over 3 places, multiply it by 9.81 newtons per kilogram. And I'm sure that this number is 0.6 because this is about 10 and that's about, 10 times less than that. So if I take the number in my calculator, it's like 61.07 divided by 1,000 to make it kilograms, multiply it by 9.81. So I'm just sort of keeping everything in my calculator. And when I do the calculation, like with all of the sort of decimals with that, what I actually get is 0.59912, which is indeed about 0.6 newtons. So that's how you do those calculations. Get the mass, make sure you know how to get to kilograms because it's always kilograms times G. G is in newtons per kilogram. And then we get to our moment of force type question. This was sort of the focus of this week's lessons. It says the cylinder in A, this one that we know its weight now is 0.6, is hung from the end A of a non-uniform bar AB. Okay, the Celsius bar is non-uniform, which means we cannot assume its mass acts in its center. The center of gravity is at its physical center, as shown in figure 3.1. The bar has length of 50 centimeters, okay, has a weight of 0.25, but it looks like they're showing us where it acts. The center of gravity of the bar is 20 centimeters from bar B. So even though this thing is 50 centimeters long, it's sort of more weight must be on this side of it because its center of gravity is closer to this. That's kind of what center of gravity tells us. The bar is pivoted at P, good. The pivot is 12 centimeters from B, that's useful. An object, X, is hung from the end B. The weight of X is adjusted until the bar is horizontal and in equilibrium. Explain what is meant by center of gravity. Open note quiz. Everybody should have got this. I told you yesterday, write this down. Write down the center of gravity definition. So hopefully everybody said it's like the point where all the weight could be thought to act, something like that, right? Whatever was on the slide yesterday. So 1 mark for explaining what is meant. And again, this is its center of gravity. So we can say, even though this is a bar with all of its mass spread out, its center of gravity is right here. We can consider all the weight of this bar to be acting right there at its center of gravity. And so that's this vector. Calculate the weight of X. We got 3 minutes to go, and I don't even think that's the last question. Then they ask us about, like, we'll put it in water, explain the origin of upthrust. We'll have to get to that on Monday, you guys. If we can calculate the weight of X, I think we're in good shape to come back on Monday, talk about these last 3 marks. This is a 24-mark paper. If you want to do corrections over the weekend, queue up the mark scheme and look at kind of, where you went wrong. Do some corrections prior to Monday. I'll ask you on Monday, hey, how many out of the 24 marks do you feel like you deserve? And you just tell me, okay? And I'll update your grade. And we'll keep working with this stuff, no worries. This is, we're getting there. All right, so calculate the weight of X. 3 minutes, here we go. If we take pivot, if we take moments about this, they tell us that it is in equilibrium, right? And so we can say, okay, this thing isn't moving any which way. About P, we've got a moment from the weight of the bar, and we could calculate how far away that is. And so we've got, this would be a moment that would make the thing go anti-clockwise, and then that cylinder that we know has this weight also is creating an anti-clockwise moment. So we've got two anti-clockwise moments. We've got a 0.6 Newton force acting how far away from this pivot? So if this is 12 centimeters away and the whole thing is 50, then it would be what? 50 minus 12, or 38 centimeters, or 0.38 meters. So there's one anti-clockwise moment from the cylinder. The bar itself has an anti-clockwise moment, this much force, acting, how far away is this from the pivot? So if this is 12 centimeters, the whole thing is 20, it would be 8 centimeters, right? Like this distance here would be 8, so 0.08 meters. So the total anti-clockwise moment is 0.6 times 0.38, 0.228 from that. A quarter of 0.08 is 0.02 from that. 0.02 plus 0.228 equals 0.248 Newton meters of anti-clockwise moment. That's got to be balanced by this moment. So if I've got 0.248 Newton meters of anti-clockwise moment, that equals the clockwise moment from this guy. It has some weight, we'll call it X, and this thing is 12 centimeters away, so 0.12 meters. Divide each side by that. I solve, X must be 2 newtons, 2.0 newtons. Is that what they wanted, the weight or the mass? There it is, the weight of it is 2.0 newtons. This has been another quiz day with Dr. Schleif. We'll see you next time.